All right, today we're talking about Chapter 11, Section 6, and events involving not, and, or, and then odds. And that just doesn't seem like a well-constructed sentence, does it? Maybe I just read it weird, but it will make sense when we get into the material here. Now, there are a couple things about this section that I feel like might overcomplicate things. So I'm going to try my best to put it into words that I feel like you will understand better. And we'll start right here with the rules of the complement rules of probability. All right. So it's called complement, COMPLEMENT, the complement rules. And looking at the top, we'll start up here. So the probability that an event E will not occur. All right. Now again, looking at this, it's just, and there's nothing wrong with it, and it is technically correct, but it's just, I feel like it's not how many people think. This is very mathematical, very rigorous, and not many people think like that. But anyways, the probability that an event E will not occur is equal to 1 minus the probability that it will occur, right? Now let's skip over this real quick and let's go down here to the second bullet point. So the probability that an event E will occur is equal to 1 minus the probability that it will not occur, all right? Now all this 1 minus stuff, and again, like I said, it is technically correct, but let's use a real life example. There are many sports fans, and let's go with basketball, shooting free throws. Right. So hopefully everyone's familiar with shooting a free throw. If I were to say, what is the probability that this basketball player will not hit the free throw? Right. So will not. So we're looking at the probability that they will not. Right. What it's saying is well, the probability that we will not hit the free throw is 1 minus the probability of that event. And we'll just put let's put F for free throw. Okay, so it's 1 minus the probability of them hitting the free throw. All right. Well, if I were to actually put numbers in here, well, I would say 1 minus the probability of them hitting a free throw. Well, let's say that they shoot 80% at the free throw line. All right. Well, 80% in our decimal form is 0.8. And so therefore, obviously, it's just going to be 0.2 or 20% chance that they do not hit a free throw. So again, there's nothing wrong with this notation. It is accurate. It is rigorous, but putting it more into our language here, I feel like this makes it a little bit easier to understand. It is technically 1 minus the probability of it. It just I feel like especially for this class, since it's not a very rigorous mathematical course, um, I should try to reword it a little bit. All right, now let's actually go to some examples that are specifically catered to this idea as beyond my basketball example. So example 1 reads, if you are dealt one card from a 52 card deck, find the probability that you are not dealt a queen. Okay, well, if I want to find the probability that I'm not dealt a queen, so there are 52 cards in this deck. Well, how many queens are there in a deck of cards? Well, there's going to be 4 queens. One moment. All right. There are 4 queens. So I know that there is 52 cards in the deck. Okay. And I know that there are 4 queens. So how do I figure out the probability that I'm not dealt the queen? And again, this I feel like we this can really overcomplicate things really fast. But you could think of it like this. Well, what is my probability that I am dealt a queen? Okay. Well, the probability that I am dealt a queen is going to be 4 over 52, or in other words, what 2, 26, 113. So a 1 in 13 chance that I am dealt a queen. Let's erase this and move this up a little bit. Okay. So there's a 1 in 13 chance that I do deal a queen. Well, what is my probability that I'm not dealt a queen? Well, then what I'll do is I'll say, well, it's going to be 1 minus 1 over 13, right? 1 minus the probability that I am dealt a queen. Well, 1 minus 13, I'm sorry, 1 minus 1 over 13. Well, I mean, this is pretty simple to do, but if we want to think of 1 as with a denominator of a 13, we can say 13 over 13, right? That's the same thing as 1. And then 13 minus 1 is 12. So there is a 12/13th chance that I am not dealt a queen. Now, again, the textbook does go into actually using the p's and not p's, and I'll go and put that into the notes. But like I said, I just feel like sometimes it's just the notation's there, and it might overcomplicate things a little bit, especially if you're trying to zoom through your homework and have yourself a Thanksgiving dinner. Right. So uh, the next example we have, starting up here, it reads, it may surprise you to see the data showing how little actual football there is in a televised National Football League game. The circle graph in Figure 6 shows a time breakdown in minutes for various aspects of an average 190-minute NFL TV broadcast. What is the probability that a minute of the broadcast is not devoted to game action or actual football? Okay, so we're talking about 190 minutes, a 190-minute telecast. Well, how much of that 190 minutes is actual game action? Well, it says it's 11 minutes, right? From the snap of the ball to the whistle being blown, it's only 11 minutes. So how much what was it? What was the probability that a minute of the broadcast is not devoted to game action? Okay, well, if the game action is 11 minutes, well, the game action is 11 over what 190 minutes? Okay, that's the game action. Well, what's the probability that we are not what is it? That a minute of the broadcast is not devoted to game action? Well, it's just going to be 1 minus 11 over 190. Or again, just to kind of make the arithmetic kind of easy, at least easier to look at. That's just, if I want to rewrite 1 as a fraction, we could do it like this, and then it makes it easy. 190 minus 11 is 179. So 179 over 190. Right, so the probability that that a minute of broadcast is not devoted to a game of action is 179 over 190. And real quickly, let's go back. I've said it earlier, but I didn't really expand on it. When we say complement, if you recall, when we were doing complements with our sets, the complement was basically the other side, right? The complement of a complement is everything that is not in A. So whenever we talk about complement here, and again, it might just be more stuff that just kind of fills your head and makes you more confused. So if you don't catch it right now, don't worry about it. Don't spend too much time on it. But when we talk about the complement, well, if the game time is 11 over 190, then the complement of that, right, the other side of that fraction to make it a whole number is 179 over 90, right? So if you add these two numbers together, you get a whole number. So that's why we say the complement. And again, if you don't get it, don't worry about it, or at least that concept right now, using the word complement. It's not. I think you can get away with really not understanding that, because to me, I feel like this concept behind this is more important than the actual wording. And we'll just keep it like that. Right. So more circle graph. Let's see. Let's go ahead and also snip this and put this here, just so you guys can see again the notation that the textbook is using the probability notation there. All right, so same concept here, same type of problem. The circle graph shows the distribution by age group of the 214 million car drivers in the U.S., with all numbers rounded to the nearest million. If one driver is randomly selected from this population, find the probability that the person is less than 80 years old. Good grief, I don't want to share the road with an 80-year-old, right? I know some of you are probably like, well, my grandfather's 80 years old. He can drive, but whatever. Uh, it's not my point. My point is, let's get to this. Um, what was I saying? Okay, so what is the probability that the person is less than 80 years old? Okay, well, let's first of all look at the probability that they are 80 over 80. Okay, and so it appears that there are 8 million people that are over the age of 80. 8 out of 214. Okay, so 8 out of 214 is that probability. So to figure out the probability that we are less than 80 years old would be 1 minus that probability, which is 8 over what, 214. Okay, and then again, let's actually move this over. All right, and it's not necessary to do this. I think this is definitely something you can probably do in your head, but just to be very thorough here, I'm going to again change this 1 to a 214 over 214. Just because I feel like adding, well, in this particular case, I guess, subtracting fractions is a lot easy for a lot of people if they actually see the fractions as opposed to seeing a 1 there. All right, well, 214 minus 8 is 206. So 206 over 214, and that reduces to 103 over 107, and 103 is a prime, I'm sure. So 103, let's put this down a little bit more. Okay, so there's a 103 over 107 chance that the person driving is less than 80 years old. Okay, so again, we just talk about complement. So all we're basically doing is just figuring out the other side, right? We figure out how much something is, the probability of something, and then take the other side of the pie there. Like the other side of 8 over 214 to make it a whole number would be 206 over 214. And again, I'll go and put the probability notation on there. Actually, I think I missnipped that a little bit. All right, so the next concept we have is mutual exclusivity. Okay, now we've kind of talked about this concept before in different terms, um, but if it isn't possible for event A and B to occur simultaneously, the events are said to be mutually exclusive. So the example up here given is, well, if we have a 52 card deck and I want to figure out, the probability of drawing a king and a queen, again, king and a queen, but I can only draw one card, well, then they're mutually exclusive. Neither can happen. Okay, well, not neither, but we cannot do it simultaneously since we're drawing one card. Now, again, breaking down the probabilities here, um, in our probability notation, or not probability, but set notation. So if A and B are mutually exclusive events, then we say that the probability of A or B, right? So if we say, what is the probability that I draw a king or a queen? Well, then what I do is I add those probabilities together, right? And of course, our set notation that we probably have memory hold because it's been a while since we've done it. The probability of A union B is the same thing as the probability of A plus probability of B. And again, this is the same thing. If you recall, the OR just corresponds with the union symbol. Right? So let's go ahead and look at an example like this. Okay, so I think I think I said this problem on accident. So if one card is randomly selected from a deck of cards, what is the probability of selecting a king or a queen? Alrighty. Well, if we have a 52 card deck, recall that there are 4 kings, one of each suit, and there are 4 queens, one of each suit. Okay. Well, 4 kings, then the probability of pulling a king is going to be 4 out of 52. Okay. And then plus the probability of drawing a queen is going to be 4 out of 52. Let's fix up this 4 just a little bit. right? Well, then 4 plus 4 is 8, 8 over 52, or what? 4, 26, 2, 13, so 2 13th, 2 over 13. That is a probability of me selecting a king or a queen. So all we're doing is just adding those probabilities together. And to keep in line, let's go ahead and snip this as well. It's working out pretty nicely. I can actually do the computation and do give you the textbook solution, since the textbook solutions are so small. All right. So next up, we're going to talk about the concept of uh, probabilities with the events that are not mutually exclusive. So I think I should probably give this whole page a snip because it gives an example before our example. Let's go ahead and take the cards over here. Oh shoot. All right. So again, this is another concept that we've kind of talked about before. It's when we subtract the intersection. So let me see if I can find exactly where. All right. So the example given here is the probability that we draw a diamond card and the probability that we draw a picture card. Okay. So the way this works is, well, what is the probability that we draw a diamond card? Well, again, in a 52 card deck of cards, 13 of them are diamond, right? Because there are 4 suits, so 52 divided by 4. So there's a 13 over 52 chance that I draw a diamond. Okay. Well, I also want to see, I'm trying to draw I want to know the probability of drawing a diamond and the probability of drawing a face card. Well, face cards, again, there are 4. Is there 4? No, there's 3. Sorry, there are 3 face cards in each suit. Jack, Queen, King. All right, so 3, 6, 9, 12. So it would be 13 over 52. Okay, that's the probability of drawing a diamond, plus 12 over 52, the probability of drawing a face card. Okay. Now here's where our notation over here really helps us out. We then are going to subtract the intersection of A and B. Okay, and in our case, A are diamonds and B are face cards. Well, there are 3 face cards in the diamond suit, right? Jack, Queen, King. So I'm going to subtract that set. And of course that makes sense because if I were just to add the probability of drawing a diamond plus the probability of drawing a picture card, right? And if I said it was 13 over 52 plus 12 over 52, well, that's 25 over 52. That's almost 50%, right? Well, that doesn't make sense in a 52 card deck of cards because I can only draw. I mean, it doesn't make sense because the face cards are within the diamonds, and there's only 13 diamonds. So we're only looking at a 25% chance there with the diamonds, and then of course we add all the face cards up. So we subtract the face cards and the diamonds, which is just 3 over 52. And of course the arithmetic there is pretty easy. 13 plus 12 plus, 13 plus 12 minus 3. Well, that's going to be 22. And then that denominator all stays the same, right? 52. And then of course we see that there's 11 over 26 chance of drawing a diamond and a picture card. Or a picture card. Right? Now instead of doing my laser around here, let's actually do an example. Right, so no lasers here. So in a group of 25 baboons, 18 enjoy grooming their neighbors. So let's go ahead and write that out. So there are 25 total. 18 enjoy grooming neighbors. What should we do? We just put G. No. And 16 enjoy screeching wildly. So 16 enjoy screeching wildly. and 10 enjoy grooming their neighbors and screeching wildly. Okay, so we're going to have 25 total. 18 enjoy grooming, 16 enjoy screeching, and 10 enjoy, I don't want to put B for both. We'll just put GS for grooming and screeching. Okay, so where are we at? So if one baboon is selected at random from the group, find the probability that it enjoys grooming its neighbor or screeching wildly. Okay, so here is where I honestly a good example of why we have to subtract that intersection. Okay, so the problem wants us to find the probability that it enjoys grooming its neighbor or screeching wildly. Well, 18 of the 25 enjoy. I don't know why I wrote 12. 18 of the 25 enjoy grooming its neighbor. 16, so plus 16, 16 of the 25 enjoy screeching wildly. If we just stopped there, we see that we have what, 34 over 25. And that just doesn't make sense, does it? We can't possibly have more baboons that enjoy doing both of that, both of those activities more than the total number of baboons that we have. Okay, so this is why we're going to have to subtract the intersection there. So we're going to have to subtract the intersection, which is 10. So 10 over 25. All right, and this problem actually turned out just beautiful, nice and colorful. So we just add these up, right? We said 18 plus 16 is 34 minus 10, so that's 24. So 24 over 25. Right? That is the probability that we choose a baboon that enjoys doing one or the other. Good example, right? So that's why I have to subtract the intersection. That was better than me blabbering on about the cards. All right, so this one I'm going to have to put that wheel here. Another good example of what we just discussed will be this one. Alrighty, so the problem reads, Figure 11 illustrates a spinner. It is equally probable that the pointer will land on any one of the 8 regions numbered 1 through 8. If the pointer lands on a borderline, spin again. Find the probability that the pointer will stop on an even number or on a number greater than 5. Okay, so what is the probability that we'll land on an even number? So we're going to actually use the probability notation here because I don't have any other notation I could use here. So what is the probability that I have an even number? Well, looking at this wheel, I've got 2, 4, 6, and 8. All right, so there are 4 out of 8 possible even numbers. And then what was the other one? Or a number greater than 5. Okay, so we'll put probability that it is, just put G for greater than 5. So what is the probability that it's greater than 5? Well, again, it's greater than 5, so it's just numbers that are greater than 5. So 1, 2, 3, right? 6, 7, and 8. So there are 3 in 8 chances that we are greater than 5. Well, now we're going to have to subtract that intersection of even and greater than 5. Okay? Well, there are 2 numbers that are both even and that are greater than 5. So we'd say the probability of, we'll put EG, is 2/8. So what we're going to have to do here is take these numbers. So 4/8 plus 3/8. Okay, and again, that is the probability of it being even plus the probability that we are greater than 5. But we're also going to have to subtract that intersection over here, the 2 numbers that are both greater than 5 and even. So subtract 2/8. And then doing the arithmetic here, 4 plus 3 is 7, minus 2 is 5. So there is a 5/8 probability that we are even or greater than 5. All right. This table, when we looked at it in the previous section, conveniently put the numbers on there for us. They summed up the married and divorced and stuff. Oh, they didn't too. I don't know what I was thinking about then. Never mind. I'll reserve that thought. All right, so let's do some more of this. So, in here, if one person is randomly selected from the population represented in the table, find the probability that A, the person is divorced or male. Okay, so let's do A. So what is the probability that the person is divorced? Well, the probability that they're going to be divorced is going to be 26. All right, so I'm going to just look here at divorced and the total there. So 26 out of how many? 254. So the probability that they're divorced, so we're going to put P of D, so probability they're divorced, 26 over 254. Now, real quickly, we're not going to worry about reducing this fraction now because chances are we're going to be using that denominator of 254 for the other part of our probability here. And so I don't want to reduce this to what 13 and 172. Oh, 170. I'm sorry, 177. Oh, no, it's not even that. I'm losing my mind. 127. I don't want to reduce that fraction down because I'm just going to have to use 254 as a denominator for the other probability. And the other probability being the probability that they are male is 123. So 123 over 254. So real quick, let me try and explain what I was just trying to say. And you probably caught it the first time, but just in case. If I were to take this and reduce this, I would say 13 over 127. I'm second guessing myself now. 125, 250. Yeah, okay. All right. And then if I were to add 123 and 254, right? Well, let's see. You see the problem here, right? When we add fractions, we want to have the same denominator. So don't worry about reducing your fraction when you get these probabilities because you're probably going to be using that denominator anyways, and so we'll reduce at the end. Anyway, so the probability that they're divorced and the probability that they're male, we have that. And we're going to have to subtract the probability that they are divorced and male. So probability that they are divorced and male. Okay, and again, we have a nice handy chart here. Well, 11 of them. So 11 out of 254. Okay. So the arithmetic here is just going to be 26 over 254 plus 123 over 254. And then we're going to subtract that intersection there. And so the arithmetic here, 26 plus 123, 9, 149, and 149 minus 11 is 138. Okay, so there's a 138 over 254 probability that they are divorced or male, and I bet that actually reduces. They're both even, so we got 69 over 127. And it's 3 go? No, 3 didn't go on the 127. All right, so that is that probability for A. And let's do B. All right, so B, we want to find the probability that the person is married or divorced. Okay, so This is going to be just like, our first two examples, huh? So what is the probability that they're married? So the probability they're married is going to be 133 over 254. And what is the probability that they are divorced? That's going to be 26, equal sign there, over 254. Okay. Now again, all we're wanting to know is the probability that they're married or divorced. And so we're just going to look at, well, let's look at the total number of married and the total number of divorced. All right. There's no there's no overlap there, right? There's no intersection there. So all we have to do is just add those probabilities up. So it just becomes 133 over 254 plus 26 over 254. A lot of times I say something and my hand writes something different, and I don't know why that is. Anyways, we got 159 over 254. I don't think that reduces. Okay. Oh, okay. So actually, real quickly, the problem reads express probabilities as simplified fractions and as a decimal. So let's go ahead and round this to a decimal. So if I round that to a decimal, it would be 69 divided by 127. Rounded to the nearest hundredth. So nearest hundredth means I'm just going to two decimal places. So 0.54. And on this problem, 159 divided by 254, it is 0.63. And I'm wondering if the previous problems were like that and I didn't read it. No, it doesn't say anything about decimals. Okay, good. All right, now the last part of this section could be kind of confusing, right? And it's odds. This is probably going to be the most confusing part of this section, hopefully. But odds. Now, the way odds work, all right, it's not the same as the probability. It's basically, um, let's see. If I said, what are the odds? And matter of fact, I'm pretty sure the next example is an actual dice example. If I said, what are the odds that I roll a 1 on a six-sided die? Okay. Well, you might say, well, that's 1 in 6. Okay. Well, that is incorrect because we're using the term odds now, right? Now, odds are used quite often, especially in gambling. And it's basically what is the probability that something happens divided by the probability that it doesn't happen. So I'm certain you guys might have heard like, boxing matches or big upsets or something. They might say the odds are 1 in 23 chance. Okay. So for our six-sided die, the odds it lands on 1 is an actual, the odds are 1 in 5. Okay. The probability would be 1 in 6, yes. But the odds are 1 in 5 because there is one outcome that lands on 1, right? And there are 5 outcomes that land on not 1. So you just basically you literally use those numbers. The odds we land on the number we're wanting divided by the odds or divided by the number of not probabilities, the number of times I can land on not 1. So again, more mathematical jargon, but at least this time it does kind of come in handy, and this time it is needed. Okay, so unlike the first time we had this notation, I was like, yeah, you guys kind of think your way through that one. I mean, you can in this one as well, but I feel like this notation is a lot easier now. So if P of E is a probability of an event E occurring, then what we're going to do is we're going to say, well, what is the probability of that event? Okay, and then we're going to divide it by the probability of not that event. And then the other side, the odds against our event, well, then the odds against our event is going to be the probability of that event not happening divided by the probability of that event happening. And we're still going to use the numbers, 1 and 6, for the 1 in 6 chance, but that's how odds breaks down. It's when you add them up, when you add up both sides of the odds, let's do an example so I can show you, because we actually use the colon. Right. So this example, I'm pretty sure I can fit them both on here. You roll a single six-sided die. So find the odds in favor of rolling a 2. So let's actually go ahead and bring that notation that I was talking about. Let's bring it over to this example so we can follow along. Okay. All right, so again, looking at example 8, roll a single six-sided die. Find the odds in favor of rolling a 2. Okay, so in favor of, we're going to be looking at the first probability of odds concept. Well, it's going to be the probability of my event happening. Okay, so what is the probability that I roll a 2? Well, it's going to be 1 in 6. Okay, so there's a 1 in 6 chance that I roll a 2. Okay, what is the probability of it not happening? Well, if it's 1 in 6 that I roll a 2, then it's going to be a 5 in 6 chance that I do not roll a 2. Right? And real quickly, this probably looks intimidating. It looks ridiculous. It is something that you probably don't want to mess with. It is something that even my calculus students are like, I don't like fractions over fractions. I hate fractions, and I especially hate fractions over a fraction. But if you recall, this is the same thing as saying 1 over 6, and then we're going to put our division symbol here, 5 over 6, which, as you recall, is the same thing as saying 1 over 6, and then we multiply by the reciprocal, which is 6 over 5. Okay, and what is 1 over 6 times 6 over 5? Well, the 6's cancel. Whenever you divide fractions, right? So if I say divided by 5/6, well, I change the division sign to a multiplication sign, and then I flip this fraction. Are you not familiar with that concept? Okay. Well, there it is. Whenever you're dividing fractions, you basically to do the arithmetic behind it, uh, you multiply by the reciprocal. Okay. hmm Uh, do it a couple times, and it'll become second nature to you. But like I said, going from this, where you're like fraction over fraction, is horrible. And then if we rewrite it like this, you're like, oh, okay, well that's easy because now I know that I can multiply by the reciprocal and get to here. Anyways, doing the arithmetic here, I've got my sixes cancel, so it just becomes rather. We'll put it in green. 1 over 5. Okay. So the odds in favor of rolling a 2 are 1 in 5. Or, I'm sorry, 1 to 5 is how it would be read more or less. Okay. Um, and actually, let's actually go ahead and let the textbook say it more succinctly. And we're going to make it a little bit larger so we can read it. But this is how odds are written. And again, at least I know in Tennessee, um, all my friends are sports gambling now, and so it helps to know the lingo. So the odds in favor of rolling 2 are 1 over 5. The ratio there, 1 over 5, is usually written 1 with a colon 5, and it is read 1 to 5. So thus the odds in rolling a 2 are 1 to 5. And again, the difference between odds and probability is the odds. All right, you basically say the odds that what you want to happen happens, and then you say 2, well, 2 what? The number of times what you want to happen doesn't happen. So the odds that I roll a 2, there's only one chance to happen that I do, and there are 5 chances that I don't. So we say 1 to 5. And then we can easily do B, find the odds against rolling a 2. Well, if the odds of rolling a 2 are 1 to 5, then the odds against are going to be 5 to 1. It's just the other side. And, let's actually, yeah, we can snip this and put that there as well. Put it over here. Okay. And again, it's just the other side, or the complement, you can kind of say. I think, okay, no, that's not the last one. We have one more after this one. Alrighty, so next up we're going to talk about winning an SUV. Alrighty, so the winner of a raffle will receive a new sports utility vehicle. If 500 raffle tickets were sold and you purchased 10 tickets, what are the odds against you're winning the car? So again, against is basically the same thing. Let's go back. We can just look at this one. The odds against are basically the exact same kind of concept, except you just basically flip it, right? So your numerator is going to be what you're looking for. If we are looking for odds in favor of, then that's the numerator. If you're saying odds against, well, that's your numerator. So we're going to talk about what are the odds that I don't win an SUV. Well, what are the odds that I don't win the SUV? Well, if we bought 10 tickets, okay, so what are the odds that I do win the SUV? Well, if I bought 10 tickets and it was 10 tickets, yeah, 10 tickets, and there are 500 tickets that actually sold, well then the probability of me winning is going to be, we'll just write like this, 10 over 500, that can be reduced to 1 over 50. Okay, so that is the probability of me winning. So if I wanted to figure out, well, okay, well, what's the probability of me, what was it? It was the odds against. Well, what are the odds against me winning the SUV? Well, then, if 1 over 50 is the odds of me winning, then the odds against it are 49 over 50. Okay, so 49 over 50 is the odds I don't win. 1 over 50 is the odds that I do win. And again, we can go ahead and rewrite this something like this. I don't know why. Over 50, which we know that we can rewrite that as 49 over 50 times 50 over 1. We know that these cancel, so we end up with 49 over 1, or you don't say 49. Again, you say this as 40. There we go. 49 colon 1. All right. So my odds against me win the SUV are 49 to 1. Okay. So for every 49 times that I don't win the SUV, I will win it 1 time. And again, that's basically just what that means. All right. And lastly, we're going to be talking about the odds to probability, and this is a super duper easy formula. It's another one of those things that you can just kind of figure up in your head. Honestly, I don't feel like I need to do too much calculations here. So we'll just put the solution here as well. We'll just put this all on top of each other. Okay, so let's start with the sandy area up top, talking about the odds to probability. So if the odds in favor of event E are A to B, right? So again, if we say A to B, this is A, the first one, and then B is the second one, obviously, yes? So if the odds in favor of event E are A to B, then the probability of the event is given by A divided by the A plus B. So if we just follow along with that formula, well, the odds in favor of a particular horse winning a race are 2 to 5. What is the probability that this horse will win the race? Well, 2 to 5, 2 plus 5 is 7, and that just becomes the denominator. And then the numerator is the first number. So it's 2 over 7, and that's what we see down here. Okay, and that's just the odds of probability. Um, I got nothing on that one. And I'm pretty sure that does conclude. Yes, that concludes today's lecture.